Hi, my name is Chris, and I'm a postdoc and associated member of ML4Q, and you're listening to ML4Q&A, a show where members from the Matter and Light for Quantum Computer cluster answer questions about their work in the cluster, their research, and the future of quantum. In this episode, I'm talking to Rami Barends, recently appointed head of the Institute for Functional Quantum Systems at Forschungszentrum Jülich, and associate members of ML4Q. We will talk about his research on superconducting circuits and the long way from his PhD work on superconducting detectors for astrophysics to demonstrating beyond classical computation with superconducting qubits at Google. We will talk about research at university versus research at Google and his plans for setting up his new group at the Institute for Functional Quantum Systems. So, at any rate, I'm very excited to have Rami Barends on the podcast today, because he's like a very recent addition to the Jülich quantum computing effort, and quote unquote brain gain from California. We will talk about Rami's career, his research and plans in Jülich, and the future of quantum. Rami studied at the Technical University of Delft, did his PhD in the group of Cosmo Nanoscience, did a postdoc in UCSB in the group of John Martinis, and then the group of John Martinis joined Google in the Artificial Intelligence Lab. And now Rami comes to Jülich to head the PGI 13, which will be the institute, or is the Institute for Functional Quantum Systems. So Rami, we usually discuss people's career a little bit because it's interesting for students and more junior researchers. Let's start with your PhD. You did your PhD in the group of Cosmo Nanoscience with Teun Klapwijk. What is Cosmo Nanoscience?
Yeah, that's a really good question. So maybe I should go back to what we did in the group of Teun Klapwijk. And what we were doing was using superconducting systems to build astronomical detectors. And what you then have is basically light from stars or planets or gas clouds. Just, you know, they travel for many years, arrive at some dish, whether it's in the Atacama Desert or in space, and are absorbed by a superconducting circuit, whether it's a Josephson junction or a little thin wire of a superconducting material that then heats up, and then you can measure a difference in resistance. So what you then have is that the fact that electrons basically respond to those photons all the way from space is kind of a marriage between what happens at the nanoscale to make a detectable signal, which you can use to say something about the cosmos. So it's kind of it's really interesting how kind of information about the universe in the end gets carried by, you know, paired electrons or other effects that you read out mesoscopically at the nanoscale, the mesoscale. So that's the idea about Cosmo Nanoscience, that you really develop nanotechnology and to essentially build a detector to learn about the universe.
So as researchers, when we start our PhD, we are often really influenced by our PhD supervisor, right? Yeah. And Teun Klapwijk is, on the one hand, known for building these detectors, which is engineering focused, but he's also known for really fundamental contributions to understanding the proximity effect and superconductivity. Yeah. Did this influence you early on?
Yeah, definitely. So, I actually enrolled in Teun Klapwijk even before my PhD. I did my master's there. I did a master's project. And in that project, the idea was to take a small wire and to have light come into that, and it will heat up and you get a measurable resistance. This is called a hot electron bolometer. And at that point, I was actually amazed by the fact that indeed, learning about electrons will allow you to build sensors for space. And I think Teun's approach was very, very clarifying, because he would ask himself, I build a device, what is the life of an electron? Whether it's, in a, non-trivial material, or, for example, high resistivity superconductors, or whether it's under irradiation or under some form of external pressure. And that simple question, what's the life of an electron in a certain system, has profound implications. And I think that is something that he said also guided his research through many layers.
And maybe to me, the important question is, of course, we do fundamental physics when we do quantum information science, let's say, and sometimes discover fundamentally new or interesting things. Do you think it's that we do fundamental physics differently if we always have an application in mind to guide us?
Yes, most definitely. And I think one way to maybe look at this is to look, three scientists, Niels Bohr, Thomas Edison, and Louis Pasteur. Right? These three people have made major contributions to science and technology for mankind. But they're different. They're really different types of working. So Niels Bohr was very much into the theory behind quantum mechanics, and in fact, we're trying to build the systems that implement like some of his ideas. Thomas Edison was somebody who was not so much inventing. It was not like Maxwell, right, inventing new theories. But he ended up building lamps and building power grids, right? He was a builder. And then we have Louis Pasteur. And with Louis Pasteur, it's also a different thing. So Louis Pasteur saw a problem, right? Milk, goes bad quickly. And turns out that simple question, like how can I stop milk from spoiling, ended up making him one of the fathers of microbiology. So Louis Pasteur is somebody who ended up doing really fundamental science, but with driven by a specific problem. And that's different than Niels Bohr, and it's different to Thomas Edison. So yes, if we have a specific application in mind, we would be doing research differently. And it's not worse or better, it's just different. And I think that is important to keep in mind, that you have these three different ways of pushing technology and research.
So today, because we usually tell people that we want to build a quantum computer, right? So that means that we are in the Pasteur camp, right? That we have a clear goal in mind, and then maybe we do some science along the way.
Well, I could return the question and ask you, well, what do we want to use the quantum computer for?
Yeah, I mean, there's people who would say that indeed we would discover maybe new physics, like understand high TC superconductivity, or whatever understanding means, like being able to simulate a system where it arises, or so on the one hand, to further our understanding of complicated quantum systems.
Yeah, but then the question is, well, what do you need to build to get there? And I think one of the answers is you want to build a large-scale error-corrected quantum computer, and that's a big task.
Yeah, for sure. Maybe to get more in that direction. So the focus both on fundamental physics and hardcore engineering is also there in the work of John Martinis, I think, from early on, right? So you after the work with Teun on detectors, you joined the group of John Martinis. Did you know him before? How did you choose John Martinis as the next step?
Yeah, so I knew of John's work, and I met him at a conference, I mean, it's also important to realize that I was looking for a PhD position in 2009, 2010, and at that point, superconducting qubits were not like it's not where things are right now. There were problems with coherence, there were problems with scaling, there were problems with materials, and with Teun, with these resonators for astronomical detectors, I was also looking at these processes, right? So you have losses in a resonator that affects your Q factor. In a qubit, we call that T1, right? The energy coherence time. In the resonator, you have phase noise, right? The resonator phase, wobbles around. In a qubit, you would have that the state starts to dephase. So that's a T2 process. And we were building resonators that were working at 5, 6, 7 gigahertz, which is exactly the frequency domain people park their qubits at, right? At least, most of them. So the technical questions are different, but the underlying physics was the same. And people made lofty promises back then also about quantum computing. And I thought, well, I'd like to find out, let me just join it and see how that goes. And I think John Martinis had indeed a big focus on the engineering aspects. And his aim was to really build something that works. And that really connected to me well. So I applied, and I ended up there as a postdoc, originally for 2 years.
Yeah, and you stayed for much longer.
Yeah. So in the first 2 years, I think we ended up fixing. It's quite interesting. So because I knew from my background is that if you put a superconducting film on a piece of silicon or sapphire, it will start detecting radiation, right? And the same thing is whether any etch and qubit out of it. So the first, I think, project I did there is to clean up the experimental stage in John's lab and to really get rid of external magnetic fields, external stray radiation. So 4K radiation turns out to be a major problem. And suddenly the quality factors were much better. So it turned out people were measuring not so much the limiting factors of their materials, but of their experimental setups. And when we realized that, we could make better qubits. And I think we started also building transmon qubits. So I renewed the the postdoc for another year because things are going well. And then we made this cross-shaped device, and we hit 40 microseconds of T1. So I thought, well, let me add another year to my postdoc because it's going well. And at that point we started to make actually devices that consisted of 2, 3, 4, 5 qubits, up to 9 qubits. So at that point, we knew we had something that worked. The foundations of that, what we were building there, really worked. And so that's one of the reasons I stayed so long for the postdoc.
That's very cool. Let's maybe take a quick step back for the listeners and talk just very briefly about the basics of superconducting qubits. What should people think of when they think of a superconducting qubit? Can we condense it down for non-experts?
Yes. So one of the beautiful things about superconductivity is that you have an Avogadro number of electrons. If you cool the system down, condense into a single microscopic state, right? And that means you can describe that and that whole ocean of electrons with a single energy parameter and a single phase. And that's on one superconducting island. So if you would have another superconducting island, you would have, of the same material, you would have the same energy parameter, but you have different phases. And if you would connect them through something that's called a weak link, you would have a supercurrent flowing between these two superconducting islands to equalize the phase. So it depends on the phase. So now you have a current, and therefore an inductance associated with it, that depends on the quantum property, namely the phase. Now, if you put a capacitor also in parallel, which two metal islands already do, you would have basically a circuit consisting of a capacitor and a Josephson junction, which is inductive. So now you have basically built a superconducting quantum electrical circuit. And they consist of a capacitor, of a Josephson junction, and you can also put a lumped element inductor. And basically pretty much all the superconducting circuits or superconducting qubits out there are one or another, concoction of these three elements: a capacitor, a Josephson junction, and in some cases an inductor.
Yeah, and I think what's important to keep in mind there is you said that there's a macroscopic number of electrons. So these qubits are artificial atoms in a sense because they have well-defined quantum levels, but they are visible to the naked eye. Like you can, we're really talking about something that is not atomic in scale, but rather really. I mean, they're small, like I don't know, half a millimeter or.
Well, in
like
principle,
this,
I mean, this superconducting island can be like arbitrarily sized, basically. And the advantages what you said is you can make your qubits quite large, and that makes them easy to couple to, easy to route control wiring around it, easy to add in control electronics or control wiring for readout, for control, for coupling, the whole thing. And because your system is big. And you can also change the shape of this superconducting island. So you can make interdigitated capacitors, you can make longer waveguides. So it's very flexible. And it's also compatible with microfabrication, so you can go to a clean room and essentially also stencil these qubits on a roll or in a grid. So it has the elements of scaling and the versatility of arbitrary connectivity to some level in it. And that's, I think, a big advantage of using superconducting systems to do quantum computing.
I, of course, agree. I should mention for the listeners maybe that I also did my PhD in superconducting qubits, so I'm a little bit biased towards them as well. I also think that the larger scale of the superconducting qubits is really not a disadvantage. In a sense, all the good superconducting qubits right now are pretty large. And sometimes people say that quantum dots are the much better qubits, for example, electronic quantum dots, because they are so much smaller. But currently the superconducting qubits are really at a nice sweet spot where the wiring and the qubits are kind of a similar size. Well, even if you can make quantum dots of like 100 nanometers size or something, currently, eventually you need to take the wires out and fan out and interconnect. So there's a lot of challenges there. Even if you want to have smaller qubits, you also need to package the whole thing eventually to have a processor that can be connected to wires.
Well, yeah, and I what I love about this is that nature is fundamentally quantum mechanical, right? So if you put an atom or an ion somewhere, it will behave quantum mechanically, and you can use it for quantum computing. But to use it, so nature is a beautiful, I think, example and inspiration here. But in order to make something you really want to adjust and use, and for example have tuning of the frequency rapidly, you kind of want to engineer a system that can do the same thing. So that's what I love about nature. It's like, it works. The foundations work. Go and look at it. But if you want to do it yourself, go do your homework. Make a system yourself.
I think also, to me, the real beauty of superconducting qubits, and unfortunately in my day-to-day work I maybe don't get to play with this enough, is that in principle you can engineer. It's like the most circuit quantum electrodynamics, this science of superconducting circuits, is maybe the most sophisticated framework for building some arbitrary Hamiltonians, well, not entirely arbitrary, but you really have a big toolbox for realizing different Hamiltonians and systems. And we usually, use transmon qubits or some well-known form of qubit, but in principle, there's a lot of freedom to engineer there.
Yeah. Although I would say that I think the ideal recipe for a qubit, or what platform, whatever, we haven't arrived at the perfect qubit yet. So I'm partial to superconducting qubits, but I think it's interesting to also keep looking at the performance and I think especially the rate of improvement of performance of related or other technologies.
Yeah, maybe we can pick up again at your at sort of the history of your research and sort of pick up. So you joined the Martinis group, and I think what's instructive is the Martinis group at the time was already doing lots of fancy qubit experiments. A lot of first solid state experiments were done in the Martinis group, and in the beginning with phase qubits, which is a type of superconducting qubit. And I think you were instrumental in the transition to these transmon qubits and then Xmon qubits. Can you say something about that?
Yeah, so I think we were, yes, John's lab was working with phase qubits, which has, I think, one of the big advantages is that you can do high fidelity readout if you don't have quantum limited amplifiers, which I think back in the day was a strong advantage. But there are a number of other advantages. I think you needed a large capacitor, and the readout itself also led to quite some heating being generated on the chip or in other qubits. So we wanted to start working on transmon qubits. And we designed first systems, and that took a while to characterize. And I think the first system we built actually worked, but to find where the qubit was in frequency space, because we still used we built a transmon, coupled that to a phase qubit, and then used the standard phase qubit readout, and that took 3 weeks of safaring to see where the transmon was. But we ended up finding it, and it kind of worked. I think the T1 was like 1 or 1.5 microsecond. So, first device kind of worked. That's the first for me. I've never had that. But then we realized we made some mistakes in the design of the transmon, and I came up with this cross-shaped device to really make things simpler. And that turned out to work well. And the reason is because it's a very highly symmetric geometry that has basically embedded in it essentially screening from the outside, because it's so close and encompassed by ground plane. So you have basically a qubit that is essentially well insulated from the outside, but it has these 4 legs, so you can connect it to a readout resonator, you can connect it to another qubit, you can connect it to other control lines. So that was kind of a template to really be at this optimal spot where you wanna isolate your qubits, right? But you also want to control them, and that's always a bit of a fight. And with this design we were able to do that. And I think what's maybe important to mention is that during that time, people were moving to 3D transmons, and that's essentially a big cavity in which you place a Josephson junction with some big antenna pedals, and they were getting really beautiful results. I think tends to up to 100 microsecond of coherence time. They're a little harder to couple, but at that time people were focused on the fundamental question: can we make a really highly coherent qubit? And people started to move away from planar qubits, right? Where you work on a piece of silicon, you have multiple qubits on that, because they honestly thought that would be just limited. It probably wouldn't work. And in that phase, we were developing planar qubits, and that ended up working. And that's based on the cleaning up the environment, based on materials science. I think we had wonderful MBE aluminum grown, and on a good design. And what was interesting is, we reached, I think, 40 microseconds, 50 microseconds. But when we placed more qubits on the same chip, the coherence didn't tank. It didn't go bad, which is typically what happens if you put more qubits in boxes. Things start to go bad. And at that point, we realized we had at least a first step towards a scalable design here. And now we scaled it up rapidly. So in 2013, we had this cross-shaped device, and in 2014, we put 5 on our own, and that worked. And we started to work to implement quantum logic gates.
Maybe as a fun side note, I mean, you guys called this design the Xmon because of the plus or X shape.
Yeah.
And I think this is a really cool case of branding in science. In principle, it's a transmon with the different capacitor shape, right? But the name really stuck, and I think it's funny because people, I think for a while among even scientists who are not exactly experts, there was some confusion that they would distinguish between the transmon and the Xmon. And
oh no, it's the same ideal Hamiltonian. It's exactly the same ideal Hamiltonian. But then the question is, the actual Hamiltonian, if you have a qubit with a T1 of 1 microseconds, there are lots of crap terms on that Hamiltonian. All right, so your actual Hamiltonian is not the same. And we wanted to really highlight that point. Yes, the ideal Hamiltonian is just the same, but the actual Hamiltonian, is cleaner because we have less coupling to crap terms. And I think that is really a concept we wanted to get across, and I guess that worked.
Yeah, no, it was quite, I think, it was quite successful. And indeed, the scaling is then important. And I think from then on, basically, the 5-qubit chip, the 9-qubit chip, you guys just ticked off a lot of very important boxes for building a quantum computer. So let's just go through a few examples. I think maybe, so the Xmon was the first milestone that you guys just showed. Okay, we have this slightly different design, which is already somewhat extensible in an architecture. Then the next step to me, or the next really big step, was the gates at the surface cold threshold, right? Can you explain what that means?
Yeah. So with this 5-qubit device, we implemented qubit logic gates, and that's basically that you manipulate the quantum state on a local level. So that's a single qubit gate operation, but also try to create entanglement between them, and this is what we call a 2-qubit gate or an entanglement gate. And the whole challenge is to do that right, especially an entanglement gate, because that's the hard thing, because it's a 2-body problem. To do that right in a 5-qubit system. I had to do a 2-body operator correct in a 5-qubit system. And this hadn't been done that well. I think the best experiments had like 4 or 5% error in superconducting qubits. And ion traps actually at the point had really good 2-qubit gates in a 2-ion system. That's like less than 1% error. But at the time when they went to 3-ion system, the error was already at like 5%. So we were really worried that this would be a problem. So I think we used an adiabatic approach to a controlled phase, and what's interesting about that approach is that the pull shape is not so important, right? You have a certain trajectory where you put qubits close in resonance and pull them back, but the exact variation of that, or the exact amplitudes, the end result is somewhat insensitive to this. So that's a very practical approach. And using this gate, we got, I think, errors of below 1% for all pairs of this 5-qubit system. And that and the single qubit gates was, I think, 0.1%. So it's like you can do 1,000 single qubit gates and not get an error. With the entanglement, you can do over 100 gates and not do an error on average. And this was actually at the threshold for what people were thinking of when building an error-corrected quantum computer, because you need to run a certain error correction algorithm, which has a large overhead, and you have to do all these entanglement gates and all these operations to really put a bunch of physical qubits, let them act together and actually like compose or form a single logical qubit. And those requirements hadn't been met before in a system that was arguably scalable. And I think with this 5-qubit experiment, that changed, because we were able to get reliable and reproducible low errors on gates in a system that you could see scale. And that was quite, I think, it was a bit of a breakthrough, I would say.
Yeah, and at the time in the field, for sure, it was also received as such. I think I just started my PhD around the time, and there was already a lot of excitement at the March meeting at the time, which is the big conference where these results are usually presented.
Yeah,
So
that was funny, because usually those meetings where, with the superconducting qubit meeting was kind of like half filled, the room. And at some point, the room was so full, the people from the fire department came and told people to leave, partly because it became unsafe. So that was that was fun to see.
So then maybe from there, the next important step was that you guys did classical error correction on a quantum chip.
Yeah.
I would say, like I would see that, like, so you had shown that your gates are good enough, and then you went from 5 qubits to 9 qubits.
Yeah.
And you used those 9 qubits to do error correction. Can you just very briefly explain what's the main idea?
Yeah, absolutely. So the idea of error correction is that you grab a bunch of qubits and compose a logical qubit. And the way that works is you entangle qubits. So you have data qubits and measure qubits, and every cycle you would measure the state. And if there would be, and that would record a parity error. So think of the following: you have data qubit, measure qubit, data qubit, and it's quantum mechanics. So you're not allowed to look at the data qubit, right? Because that would project it. But what you can do is you can look at the parity between the two data qubits, and to do that, you have to have that qubit in the middle. Let's call it the measure qubit. Interact with the left data qubit, then interact with the right data qubit, and then you measure it. And if that measurement switches, that switch would imply a parity error. So one of the data qubits flipped. Now, you can't tell which one. But if you repeat that, right, where you have data qubit, measure qubit, measure qubit, and you repeat that, then you will be able to tell which data qubit flipped. Now, you don't know what the information was, but you will be able to say that it flipped. And you can just keep track of that until the end of you don't even need to correct it. You just keep track of that. It's like, oh, at the end of my run, I know this data qubit in this round flipped. So I can flip it back in software, and I saved my data. Now, with surface codes, this is done in a 2-dimensional array, where you correct for bit flip and for phase flip. Right, it's quantum, right? So you have 2 axes you need to correct on. Now, the 1-dimensional variant of that is you can only correct for or bit flip or phase flip. We chose to work with bit flip initially because that was what we could do. But what you do have to do is figure out how to run fast cycles of entangling gates and measurement, and we ran that, and that worked in terms of really detecting those errors. And we even applied this on a quantum state, right? Because you say, well, classical error correction, it wasn't able to correct a phase error, but it wouldn't additionally, it wouldn't destroy phase error. So we did put in a GHZ state, or like a fully entangled state in the data qubits, and try to correct that, or try to stabilize at least bit errors. And that worked. So that was, I think, one of the first demonstrations of repetitive error detection in a superconducting system using entangling gates and using fast measurements.
I think even beyond that, usually the ion trap community was always slightly ahead of the superconducting qubit community, right? It's fair to say, like, they started out earlier.
They started out
and
earlier.
They had better and more qubits for a long time. Like they reached 13 qubits around the time maybe that you guys had 5 or 9.
I think 14 even, yes.
Yeah, or maybe 14, yeah. But it's fair to say also that at this point, this repetitive error correction experiment, I think they couldn't do at the time. I think by now they have done it. But at the time, sort of superconducting qubits started to be able to do things that the sort of older and more advanced technology had not done yet, right?
As far as I understood, yes, that's true. And one of the reasons that if you would do multiple operations on an ion trap, the trap heats up, and cooling that, well, you'd have to wait. So doing fast repetitive cycles continuously is something that was technically beyond what you wanted to do.
I think they also had trouble with fast non-demolition measurements. I think that maybe that's another thing.
That's another thing.
But for sure, at some it's really an interesting point, right? Because it was for a long time that the ion traps were ahead, and that you could really always point at any superconducting qubit experiment and say, well, they did it 5 years before, and usually also better. Because
and I especially when we were doing benchmarking these gates, there's some technique called randomized benchmarking. And what you do is you put, you run a set of random gates, and at the end you apply a reversal gate that inverts the whole thing. So logically you would have done nothing, but you'd run all those gates, and all this stuff was already done in NMR, actually, even before ion traps. So.
Yes, true.
So it was good because it helped us a lot.
I think that's also the NMR thing is super interesting. Indeed, it's sort of the ancestry of quantum computing. Yeah. But the difference was that in NMR, people really didn't have single-shot readout at the time. So you couldn't take one nuclear spin and read out its state once, but you always had many of them. And so that I guess is, with the superconducting qubits, you really have one qubit and you read out that qubit at that round. Yeah. And you can say what is the state of the qubit. You don't have to average multiple rounds or multiple qubits.
No, that's correct. Single-shot measurement.
And yeah, and single-shot measurement is something that superconducting qubits really excel at, I would say. Somehow, that's maybe not necessarily something that the other systems can integrate so easily with all the other stuff they do.
Yeah, it's interesting, I think, measurement, because you have a qubit. Right now we're using something called dispersive measurements. You take a resonator, you couple it to a qubit, and that resonator you send pulses through, that gets amplified by a quantum limited amplifier, then a commercially available high electron mobility transistor amplifier, then all the way to room temperature to a control electronics to really try to, onboard decoding of that signal, all this stuff to get 1 bit of information out.
Yeah, it's really funny, like these, some of the amplifiers that we use were previously championed also for astrophysics measurements, right? At least there was astrophysics and groups that were sort of in the same frequency regime, and so there's an interesting engineering overlap.
Yeah, that's right.
So I think maybe remind me how it all went, but around the time that you guys did the 9-qubit stuff, eventually the Martinis group was sort of integrated into Google from the University of Santa Barbara.
That's right. Yeah. So I think John was approached by a number of people, and I think Google was highly interesting. At the same time, I think we were. We got our funding from the U.S. government, right? And they implicitly put a limit on the number of qubits that we could build. And that limit was apparently placed at 10. And I remember that that people were like, what the heck? It's like, we understand that you between 1 qubit and 100 million qubits for an error correcting machine, you want to put a limit somewhere. But to place it at 10, so it was clear that continuing that route was not gonna allow us to just continue to building the technology. So I think joining Google was a really, really good move at that time. It was really good, and it allowed us to continue to work.
So how does it work? How did you experience your research group being sort of corporately absorbed by a major corporation? How is that as a researcher from university?
It was an interesting experience. I had no idea about any of this stuff. I have interviews, and I had to change my visa, and we got a new lab, and we had to continue our work because we still had things running at UCSB. So it was an interesting period. but we were able to continue to work, and I would say that I think joining Google was, we essentially, we were already on a track to really try to figure out the engineering and the technology behind this, and we continued that. But I think with Google resources and also I think a really good software infrastructure and also a software infrastructure mindset. That really helped, and that helped really accelerate the development to where we're now.
So, how important are the people at the top in this context? There's John Martinis, who obviously made this brave decision to really change the way that his funding worked, and you have Hartmut Neven at Google, who was, I guess, instrumental in taking the decision to sort of fund a research group and then integrate it into the company. How does this? How important were the people at the top to making this transition work?
No, I think it's very important to make that transition work. But I would say that the seeds of this were laid before. I think John was always focused on building something that works and to engineer around something that would function. And I think that's a really healthy mindset. And Hartmut is from the other side, where he has a big background in machine learning, right? I think he was a professor in California. He started, I think, 2 companies. One of them was, I think, taken over by Google. And in Google, he also worked on Google Glass and a number of other things. And he was attracted by quantum computing at that point by annealing, because it had possible applications to machine learning. So there was always a machine learning approach to that. So you'd have engineering mindset and a application mindset here. So I think you can see there a very healthy match that really helped it. Yeah.
Yeah, it's kind of curious that the quantum computing part in Google became part of this artificial intelligence lab, right? That's what it's...
Yes, that's the name, yeah.
And is this like an obvious connection, do you think, that quantum computers will have this obvious application in artificial intelligence systems, or is this...
Well, we'll see.
Yeah.
We'll see. I mean, what's the... what can you do with a quantum computer, right? And I think there are multiple answers and at multiple levels, right? You can build an error-corrected quantum computer. There's a number of things you can do, but that's going to take a while. So then you ask yourself, well, what can we do now? And I think the answers there are less clear. I think with artificial intelligence, the slight issue is that you're competing with essentially, 30 years of improvements and work in classical systems. So that is challenging to have that, to first overcome that and then to go beyond that. And
the recent developments in AI stuff are all tied to GPUs, right?
Yeah.
Mostly. And Google also had some cool hardware developments of their own, right? This tensor processing unit, I think, is something that Google developed. So it's not only a software company; they also have some hardware.
No, that's right. They do a lot of hardware too, but they don't really. They use it for internal projects, so they don't really sell hardware.
So, okay, you guys teamed up with Google, and I think then there's another sort of transition in how the qubits worked, right? There was a change from Xmons to Gmons.
Yeah.
And that made essentially this big breakthrough then of Google and John Martinis of quantum supremacy possible, right?
Yes. So, what we use is, or what was used in Google is the tunable coupler and capacitive. So I think there's a lot of work has been done on inductive coupling, but the change was to use a capacitive coupler, and this is actually in the thesis of Charles Neal when he finished at UCSB. And that worked really well, and it worked quite fast, and it really allows you to do parallel operations. So you turn on coupling between certain parents, you turn it off with others, and that parallelization really speeds things up. All right, because if you have a fixed coupling system and you want to work on 2 qubits, you need to kind of turn off the direct neighbor. So that's 6 direct neighbors. So it becomes an 8-body operation just to do a 2-body operation. And with tunable couplers, you can avoid that. It's easier to do in practice. So that is something that really helped build a system that allowed you to have high fidelity in parallel at speed. And this is an ingredient definitely of supremacy. Yeah.
Yeah. So for the non-expert listeners, I think the point is in the previous experiments you had the qubits in a line, right? So every qubit had 2 nearest neighbors.
Yeah.
And of course that's easier than having 4 nearest neighbors that you would have in a 2D array when you put your qubits on a grid. So and for the quantum supremacy experiment, of course, you put the qubits on a 2-dimensional array of order of 50 qubits. Then.
Yeah. But it was built on top of all the technology we developed previously, right? To have the quiet environment, to have the high-quality materials. It's still cross-shaped to minimize couplings, and then to add that tunable element to really optimize things. So I think it's a cascade of breakthroughs that all compound to make a system work. And I think that also highlights the many different facets you need to actually build a system that can do something.
Do you think you guys could have built the 50-qubit quantum computer with the academic resources, or was the move to Google a game changer that allowed you to do more complicated experiments?
Well, I'm still amazed that we're able to put 9 qubits together with academic resources and get fidelities better than what was done at that time in other, better funded institutes and corporate environments. So I guess the answer is yes, with Google resources that was critical, but I think even more important is to have, I think, the right approach and the right architecture, the right mindset. And some of the experiments we did like years ago still haven't been fully reproduced in other labs, and that is, I think, interesting.
Absolutely. So let's talk a bit about quantum supremacy, because that's obviously like the really big, like.
Yeah, I think we want to call it beyond classical computing,
exactly,
right? Because I think it's an annoying word now.
or people say quantum advantage, right?
I would call it beyond classical.
So okay. What's the core result that got people so excited?
Yes. So the thing you want to do with quantum computing is to implement an algorithm, whether it's generating a state or figuring out interactions between competing ground states to simulate materials or simulate chemical interactions. One of the applications would be to figure out what catalysts you could use. But fundamentally, it all comes down to running an algorithm in a programmable quantum processor, and to do that in a way that goes outside of the possibilities of, or beyond the capabilities of, classical supercomputers. And this experiment, this beyond classical experiment, is based on sampling from a probability distribution of a highly entangled complex state. And then it comes down to, how do you build that state? Well, it has to be large. Yeah? So, 50 qubits is, you need a RAM of 2 to the power of 50, and that's kind of where the borderline of what you can do with classical computers. But it also needs to be a complex state. And for that, you need many cycles of single qubit gates and 2 qubit gates to really slush around this quantum state and really connect all these single qubits together and make a highly complex entangled state that really explores the Hilbert space of 2 to the power of 50. And that is something that requires not just a number of qubits, but it also requires a high fidelity, meaning all the gates you apply, you accumulate error whenever you do something. And to have that error be small with respect to how many cycles of gates you can do. And that combination of number of qubits and the cycle depth of your algorithm actually created a state that you could sample from, and that probability distribution you could get is no longer easy to compute on a classical supercomputer, and it would actually be outside of its capabilities. And at that point, you have to run an algorithm. Sure, it's making a random but highly complex state, and to sample its probability as a precursor to running an algorithm where you would create a state that would then, tell you something about a molecule or something. So being able to do that beyond the abilities of classical computing was a demonstration of beyond classical computing in a programmable quantum processor.
So of course afterwards there was a lot of discussion. IBM, who is a company that also does quantum computing and builds supercomputers, came out and they said, well, we can do this computation better, and it's not as supreme as publicized. But what do you see? Like, how many people designed the quantum supremacy experiment and built the computer? Like, how complicated do we have to imagine this system compared to the IBM supercomputer that was sort of the competitor?
Oh, well, I don't know much about supercomputers, classical supercomputers, so I can't tell you much about that. What I would say is that I don't think this was run, because it would be, I think they run into issues where they would have to use hard drives, and that would be extremely slow. And there's also another thing where, running a supercomputer for a while, that also burns up quite some energy, and it would be more energy efficient to just have one chip in one single dilution refrigerator and press run. So I think also in terms of energy usage, there's some advantages here.
So yeah, it's a David Goliath kind of situation, right? The supercomputer. Did you ever see any of the supercomputers that you guys used in the simulations to verify the experiment?
I haven't personally seen them, no.
Because they are bigger, right?
They're massive.
The quantum computer takes up roughly, let's say, the size of a room, a larger room with all the control electronics and.
It's about 8 by 8 meters or something, so 7 meters. Yeah.
And these supercomputers are significantly larger. Like the IT guy has to walk quite some distance to put all the cables. No, so indeed. Then maybe just a quick wrap up on some of the Google experiments. I think you afterwards also did surface code prototypes. So you demonstrated there was some experiments on demonstrating error correction, right?
Yeah, that's right. But I think one of the topics that was, I think, discovered but not addressed is back when we run this, 9 qubits on a row and do the repetition code experiment, we saw that the ability of the system to correct errors, that rate of correction was actually decreasing while we were running it. So something was deteriorating while we were running the algorithm. And one of the things we discovered was that, we use these transmon qubits, and those are weakly nonlinear qubits, meaning that the computational state is stored in 0 and 1, but there is also a 2 and a 3 and a 4, and if you're not really careful with your control pulses, you can start exciting those. And we were doing that, a little bit, but it would just accumulate, and that would essentially, to some extent, poison the system. So in the meantime, I think we worked on a reset protocol that would clean out this higher level state population, which is parasitic. And you can look at the results and see that it would work about 50% better if you would implement this leakage removal strategy. And that tells you that it's one of the dominant errors. And the reason is that leakage into these higher level states, they're long-lived. So you get errors that are correlated in time over many cycles. But it also can spread because these qubits are, couplings are turned on and off, and these higher level states start to spread. So it also leads to errors that are correlated in space. And that combo of errors correlated in space and errors correlated in time is actually one of the Achilles heels of error correction. Because the assumption of error correction is more qubits is better. So if you have local errors, you can keep correcting because the grounder ensemble will be able to push down local errors better. But correlated errors is something that can completely derail that picture. And that's why removing that leakage is something that was a critical contribution to running larger systems. I would also say that I think it was done until like 30, 40 qubits. Oh no, it's 30 qubits. So I think you see a larger system that is better behaved. So that's also what you see in the years of technology development.
Maybe just, one very quick, you had a recent really cool experiment about quasi-particles, which are broken Cooper pairs, right?
Yeah.
And I think you called it catastrophic failure events or something like this, right? Yeah. What does this, basically what you guys showed was that cosmic rays or background radiation or something can also affect the qubits, and in a way that it doesn't make single qubits fail, but that it can, make the entire processor fail, right?
That's right. Yeah, it's kind of back to the roots where, turns out that if you grab a piece of silicon or substrate and cool it down to tens of millikelvins, it will detect any energy, and that will lead to a measurable change. Even when you put a little superconducting film on it and call it a qubit. So, we saw that about every 10 seconds for the size of chips we had, the whole system would go haywire for, milliseconds on a row. So, we were constantly exposed to high energy rays, right? This is cosmic rays, or this is like, high energy particles from the sun hitting the upper atmosphere, generating muons, which then travel through your chip and deposit energy. And this deposited energy is powerful enough to break these paired electrons, right? These superconducting electrons all over the chip. And now you have these unpaired normal-like electrons, and they cause energy loss because they can absorb energy. And the quantum information is in these qubits also stored as energy. So now you have a process that's very common, right? Cosmic rays are just happening the whole time. And also background radiation that is actually capable of causing massive error on a chip-wide scale consistently. And that is catastrophic.
But do you think that just putting a big layer of lead above the chip and making sure that you don't have background radiation close to your chip, that this is will resolve the problem? Or do you think that people do we have to be worried about this, or is this something that's entirely solvable?
Well, you'd have to make your fridge out of non-radioactive parts. That's going to be tough, right? Because radioactivity is everywhere. The lead, even lead is radioactive.
Yeah, you need to use the old lead, right?
Yeah, so the only way to really suppress this is to use lead that has been at the bottom of an ocean or sea for 2,000 years, because the cosmic rays would be stopped by, a lot of water. And if they're on the surface, they would be exposed and become a little radioactive. So this is Roman lead, because the Romans used lead for their boats. And if they would load up their boat with, I don't know what, probably like olive oil or some good wine, they would throw out the lead. Now, there's a finite amount, obviously, of Roman lead. So to use that all up and to make a sealing on a fridge that itself is still radioactive because it contains steel from I don't know where, is maybe not the best approach. So, you'd have to solve it in the device itself. And I think beautifully there have been experiments done back with the superconducting resonators for astronomy that I used to work in my PhD. And they made resonators on membranes. They made them with some kind of a backplate coating, and that really helped to suppress the effects those high energy impacts have. So yeah, it's a bit back to the roots with respect to technology development. But what that really tells you is that, again, quantum computing is a specific field, but it overlaps a lot with other fields that have similar technological or scientific challenges. And one of them is these microwave kinetic inductance detectors, using superconducting resonators for astronomy.
So shall we do some quick rapid questions where you just answer either or? Like I give you two options and you quickly tell me the one that you choose. Let's start with places. So do you prefer Santa Barbara or Scheveningen?
That's a tough one. So in Santa Barbara, you can't really swim in the water. It's too cold. In Scheveningen, you can. So summer in Scheveningen beats Santa Barbara, but the other times of the year, I would be in Santa Barbara.
Science or engineering?
Yeah, both.
All right. Academia or industry?
That's a tough one. I've done both, and I'm now trying to find a hybrid model. So I would say academia, then industry, then ask yourself what you want to do.
Transmons or Xmons?
I would say that the key focus is in building a system that actually functions. I would say that is the engineering approach, and I think that's the right approach. So that is what the X means for me.
Then I do have the question here. I did write down quantum advantage or quantum supremacy, but we settled now on beyond classical computing, right? But let's ask, beyond classical computing or quantum error correction, where do you think will be the important progress for the field?
I think we'll see beautiful pilot experiments and pilot demonstration being done with quantum error correction. I think that will be coming. But the path to you can look at the estimates, and I think the minimum you need is around 10 to 50 million qubits. So the path towards building 10 million qubits is, in my mind, not clear. I would say that requires an architecture that is not just highly coherent or scalable, but also lean on control and readout. And I don't think we have it yet. So I think we'll see lots of interesting pilot demonstrations this decade, but I don't think we'll see error correction functioning to the level we needed this decade. And to keep the field going and to keep it interesting and people interested, I think we need to double down on enabling beyond classical computing for problems that are, I think, relevant. Rather than just random sampling, we need to do something with that power that we apparently are able to build. So I think this decade will be the decade of useful beyond classical computing. At least that's what I hope. And we will see what happens. And I suspect that what we discover there will be very useful for error correction, but not this decade.
Then new superconducting qubits or more superconducting qubits?
I think new as in better, yes.
All right. I think this is also really funny. I think John Martinis at the time, at one of the March meetings, he was saying, right now is not the point for making more. At the time, was not the time to make more qubits, but to make the entangling gates better.
That's right.
Yeah,
that's right.
So let's now shift gears a bit and talk a bit about your future here, and talk about how are you have learned how to build a complicated 50-ish qubit quantum computer. How are you gonna take this experience to Forschungszentrum Jülich, and what are the things you learn in sort of the software part, the hardware part, etc.?
So I think the key question that I arrived at was, how do I build a better qubit? How to build a system using that which can do something? And it starts with a very fundamental question. What's the fundamental limitation of a qubit? And I don't think we have a complete picture of that. So that's a very academic question, right? Because you have to leverage academia, PhD students, and postdocs to really figure out fundamental physics that goes on. I mean, these superconducting qubits are actually quite dirty systems. Right? They consist of substrates with oxides or residue from chemistry. You put a metal film on top with some inclusion of oxygen or magnetic impurities. You make an oxide barrier. Well, that's an amorphous barrier with inclusion of I don't know what. It's jagged. It contains configurational defects that may couple to your quantum state. So a solid state system is actually natively a dirty system. And to try to make something beautiful with that, in my mind, that's the almost artful challenge that we have as physicists, as device physicists. But then you also need to go the next step and actually build a system with that and care about things like fidelity, care about performance, care about yield, care about reproducibility. So that's very much an engineering mindset. So you need the scientific exploration where you test out new ideas and see whether it could work, but also then try to embed that in a larger system and see whether it can function. And in my mind, any way you look at this problem, you will need a team that has the a scientific exploration mindset, but also an engineering let's build it, let's get it done, let's get it working mindset. And that intermarriage is, I think, not trivial, and it's not so easy to find. And one of my ambitions is to stimulate that here in Jülich.
So you will have to also focus on education to get some new eager PhD students, master students who come with fresh eyes to the challenges.
Yes, education is I think an important part of it, because as you put, it allows you to attract new fresh minds to look at the problem in a new way, in a new light. But it also allows you to train the next generation while you're building a system. And I think that combination is very attractive. And I think that's also the right way to approach this. So in my mind, education is an important part of this, perhaps integral part of this. And that's why I think this academic/engineering approach is the right way to do it.
Maybe for a last topic, we can talk about the Chinese quantum effort, because they recently repeated the supremacy experiments with more qubits. And I think it's fair to say, I don't think they would even disagree, that it's really a repetition of the Google experiment. They didn't, it's not that they used a very different qubit type or did a very different measurement protocol, but it's really largely repeating the experiment. And you said before that in Europe we haven't done this, and even IBM and Rigetti Quantum Computing, who are other competitors in the superconducting qubit field, haven't really repeated this beyond classical computing milestone. What did the Chinese group do right? Should the other groups also do this? And what does it take to demonstrate, to master this experiment?
Yeah, I would take two things out of this, the Chinese work, and I think it's very impressive what they did. So they have a team of people that was able to go over published literature and thesis and try to piece together how you build such a system, and to actually build it and do it and run it. And I think it's amazing to see that can be done. It's really also healthy to see other people are also using this random state sampling as a benchmarking tool. That hasn't been done much yet. So I think in terms of program management and project guidance, I think this is extremely, extremely impressive done. But it also highlights, I think the Google effort achieved beyond classical computing, and it looks like the Chinese effort did, even on top of that, went a bit further to do that. And, one is sponsored by an industry, the other one is sponsored by a government. But at the core, these are quite, well-functioning teams that are kind of like organized somewhat monolithically, aimed towards a single ambitious goal. And this is something that you don't see too often, I think, in our field. And it's high risk, high reward. And apparently they feel free to do so.
Because many other research groups are stuck before 50 qubits, right? I mean, it's quite difficult to reach. I mean, people should appreciate it's actually not that people cannot build a 50 qubit quantum processor, but a 50 qubit quantum processor that will work. Like it's like many research groups at this stage would be able to have a 50 qubits on a chip and have each of them work. Maybe it would take some trials, but to have all of them work together as a 50 qubit unit, that's really a challenge that people are struggling with.
Well, I think important to highlight here is that you need quite some infrastructure, whether it's fridges, cabling, control electronics, software, and also people to really calibrate such systems. So you need quite some infrastructure to successfully run a large-scale system. But, I mean, you could also decrease the size and say, well, can you run 5 qubits well? And I think that's more of an exploratory question, but that is also not always too easy for some groups.
So will you be aiming, what kind of number of qubits will you be aiming at first when you start?
Well, we don't have the capabilities to fabricate qubits at Jülich yet. This will arrive soon, and then it starts. And we will have to build up the know-how, build up the technology, and build up the device architecture to really get something going. And I would say that while we're doing that, it's also important to keep a focus on the more fundamental aspects, to do in parallel, do research that, 3-4 years from now, you can actually merge into kind of that train towards larger scale systems. I would say, I would like to see few qubit systems next year, and then when we get that to work, to really start scaling up somewhat aggressively towards 20, 30, which is, I think, a really good size where you can still do it without too much difficulty, but really build up the whole infrastructure needed to run such systems. I mean, around 10 you can do still manually. Around 20 you need to have a better structured approach. So I think that will be also an interesting interesting crossover, which I think a lot of teams you mentioned, they haven't gotten there yet.
So in terms of the challenge, there's the software, there's the cryogenics, there's the fabrication. Which one?
There's the architecture.
And the architecture.
There's architecture. How do you build a scalable system of superconducting qubits, in this case, that is actually able to, run gates or run anything with fidelities that are performant enough. And I think for that, the error rates need to go down by on the order of a factor 10.
And do you think that there's what is the place where you would in architecture, better fabrication, material science, better cryogenics, or all the software around the quantum computer? Where do you see the key place to innovate?
I think the key limitation is the qubit itself at this point, because we've seen that we can scale systems. Large-scale systems seem to not have wonderful coherence, and smaller systems seem to be better. So there is also a problem when you scale to larger systems. And what happens is you need to bring in all the control wiring, you need to get additional layers of your chip, art flip chip, or other kinds of bonding approaches. And you add to the complexity of your system. You add more materials, you add more layers, you add more control wires, you add more stuff. And to keep that going at the level of coherence that you need is quite a challenge, and it seems that is at this point difficult. So actually you need to put it in reverse and ask yourself, how do you make a qubit that actually is already really performant without all this wiring and can scale? And I think that recipe has not been figured out yet.
Yeah, no, that sounds like an exciting.
But it goes back to the architecture. What do I actually want to build? Yeah. And I think that is where what we need to work on critically.
So you are now at the stage. You will be hiring a big team soon. So.
Well, I'll be hiring, and then I think I like to organically grow that towards a big team, not like massively.
And then take on this challenge and hopefully have a quantum computer in Europe that can rival eventually, at least be at the level of the Google and Chinese experiments.
Well, we'll see where we get. I mean, I don't. It's not my ambition to copy that stuff. I think it's my ambition to really go back to the core and figure out what you can build. So to lay the scientific and technological foundations to build a large-scale system that could do something on the path towards usefulness. And that's something that's, I think, very, very, very interesting. And I think that also addresses the key challenges we have in this field now. Can it work? This is, I think, an open question still.
Well, that's a good point to maybe end. Of course, you and I are very excited about this. Otherwise, we wouldn't have spent a lot of our lives so far working on it. So thanks a lot for this conversation. I hope that we covered most of the interesting topics. I could talk about this, of course, a lot longer because it's also my field, and that maybe showed in this podcast episode. But I hope it will also be interesting. And so anyway, thanks a lot. It was a real pleasure for me to
Thank you. Yes.